In a place as beautiful and as seismically active as Nepal, a building code isn't just a set of rules for construction, it's literally a blueprint for survival. Today, we're going to unpack the Nepal National Building Code, a document that, when it's followed, can be the crucial difference between a building that stands strong and a total disaster. Okay, let's get into it.
This statement right here, from the code's own preface, it's not just technical jargon, is it? It's a mission statement. It's a promise. The goal isn't to make buildings completely earthquake-proof, because, let's be real, that's pretty much impossible. The goal is to build structures that are survivable, and that is the core philosophy we're going to be exploring.
So why is this document so incredibly important? Well, the answer is literally right under our feet. Nepal's unique geography puts it in one of the most hazardous earthquake zones on the entire planet, a reality that came into sharp, tragic focus during the 2015 Gorkha earthquake.
And look, this isn't some temporary threat we're talking about. It's a permanent geological fact of life. Living on a major fault line means that earthquakes are not a question of if, but when. And that's exactly why a strong, scientifically sound building code isn't some kind of luxury. It's an absolute necessity for protecting lives.
Now let's get into the code's central idea, which is actually brilliant. It's not about trying to fight an earthquake's immense power head-on. You're not going to win that fight. It's about designing buildings that are smart enough to absorb and redirect that energy. It's all about building things that can bend but not break. The code balances two totally different scenarios. On one hand, you've got life safety. Think of this as the plan for the big one, that rare, massive quake. The goal here is brutally simple. Stop the building from collapsing so people can get out alive. The building might be a total loss, but lives are saved. Then, on the other hand, you have damage limitation. This is for the smaller, more frequent shakes. Here, the goal is resilience, making sure buildings can get back to use as quickly as possible.
So, the key to this whole bend, don't break idea is a concept called ductility. Now, what is that? Just think of a paperclip. You can bend it back and forth, right, multiple times before it finally snaps. That ability to deform without just shattering, that is ductility. A ductile building can sway and move with an earthquake, soaking up its energy instead of breaking apart.
Okay, so how do engineers know how strong to build? They can't just guess. The code provides a really precise formula for calculating the seismic risk for any spot in the country. And it all comes down to answering three fundamental questions.
Location, location, location. It's everything. The risk of an earthquake is not the same everywhere in the country. Some places are much hotter spots than others, and the code has to account for that.
And this map here shows you exactly what that looks like. The country is divided up into different zones, and each one gets a Z-factor. That's basically a score for how much the ground is expected to shake. A higher Z-factor means you're in a higher risk zone, and any building there has to be designed to be that much stronger.
The location is just the start. The next critical question is all about the foundation. What kind of soil is the building actually sitting on? Because it turns out, the ground beneath your feet can completely change how you experience an earthquake.
You see, the code classifies soil into 4 types, from A down to D. Building on solid rock, type A, that's the most stable you can get. But building on soft, loose soil, like type D that you find in parts of the Kathmandu Valley, well, that is a whole different ballgame. That loose soil can act like a bowl of jello, amplifying the seismic waves and making the shaking way more intense. So a building on type D soil needs a much stronger design to handle it.
Okay, so we've got the location, we know the soil. The final piece of this risk puzzle is the building's purpose, because in the aftermath of a disaster, not all buildings are created equal.
The code gives every building an importance factor. A standard house or office building, that's a class 1. But a school where hundreds of kids are gathered, that's a class 2. And it has to be built 25% stronger. And then you have the really critical stuff. Hospitals, fire stations, power plants, the places we absolutely need to be running after an earthquake, those are class 3. They're designed to be a whopping 50% stronger, to make sure they can serve the community when it matters most.
So once the engineers have calculated that specific risk, how do they actually design a building to handle it? The code lays out some incredibly smart, really elegant principles for what makes a structure resilient.
It turns out that in an earthquake, simple is safe. Symmetrical, uniform buildings, think simple boxes, they perform so much better than complex, irregular shapes. A balanced design makes sure that all those seismic forces get distributed evenly, so no single weak point takes the entire hit. And redundancy, that just means having backup systems to carry the load. So if one thing fails, others are there to pick up the slack.
Now, just like the code tells us what good design looks like, it also creates a kind of most wanted list of bad design features. These are called irregularities, and they are things that engineers have to avoid because they create predictable and often fatal weak points in a building.
First up is torsional irregularity. This happens when a building's center of mass doesn't line up with its center of strength. So when the ground shakes, instead of just swaying back and forth, the whole building twists, and this twisting motion puts enormous, often catastrophic stress on the outer columns. Next, we have re-entrant corners. You see it in buildings with complex shapes like an L or a T. During an earthquake, the different wings of the building try to move independently, and all that stress gets concentrated right at those inside corners. Those corners can literally be torn apart.
And finally, here's a really dangerous one: in-plane discontinuity. This is where a major load-bearing wall on an upper floor doesn't have a direct path down to the foundation. It's resting on a beam instead of another wall below it. It's like pulling the rug out from under a critical support, and it creates a massive, predictable point of failure.
So, we've seen the risks and the design principles, but the science of earthquakes and engineering is always getting better. A building code can't be a static document that just sits on a shelf. To be effective, it has to be a living thing, constantly evolving.
And you can see that evolution so clearly on this timeline. Nepal's code has a history of learning and adapting. The first one in 1994 was a response to the '88 quake. The tragic 2015 Gorkha earthquake provided a massive real-world stress test, and that led to a major revision in 2020. And the latest version in 2025 continues that process, getting better based on feedback from the engineers who use it every single day. Each event, each piece of new research, it makes the code smarter.
And this all leads us to our final and maybe most crucial question. Having a world-class building code is one thing, but a code is just words on paper. The real challenge, the one that ultimately saves lives, is making sure that these principles are understood, enforced, and actually built into every single home, school, and hospital. That is the bridge we have to cross from theory to a truly resilient reality.